Hello, friend. Tonight, we're diving into one of the most mysterious and elegant ideas in modern physics, string theory. Together, we'll take it step by step, from the basics to the edges of what we know. So find a quiet place, get comfortable, and let's explore the threads that might hold the universe together. Chapter 1. Introduction to String Theory. At its core, string theory is a theoretical framework that attempts to describe all fundamental particles and forces in nature as different manifestations of a single underlying structure, one-dimensional strings. These strings are unimaginably small, and instead of being point-like, as particles are treated in the standard model of particle physics, they possess length but no other internal structure. Their behavior, how they vibrate, how they move through space, how they interact, is governed by the principles of quantum mechanics and relativity, woven together in a way that aims to unify all known forces, including gravity. The concept of strings as the most fundamental building blocks is a departure from the standard model, which treats particles such as electrons, quarks, and neutrinos as point-like entities with no spatial extent. In contrast, in string theory, these particles are viewed as different vibrational states of a single type of string. Just as a single guitar string can produce multiple musical notes depending on how it vibrates, a single type of fundamental string can manifest as different particles depending on its mode of vibration. This idea may sound abstract, but it has deep roots in both mathematics and physics. In the early days of particle physics, researchers were struck by the growing number of particles being discovered in particle accelerators. These particles seem to form families and follow certain patterns, much like the harmonics of vibrating strings. This suggested that there might be a more fundamental layer underlying what appeared to be a zoo of unrelated particles. Historically, string theory did not begin as an attempt to unify all forces. Its earliest incarnation emerged in the late 1960s as a model to explain the strong nuclear force. At the time, the observed behavior of hadrons, particles like protons and neutrons, displayed resonances and patterns in scattering experiments that were difficult to explain with existing theories. Italian physicist Gabriele Veneziano proposed a mathematical formula that remarkably captured many of these features. The formula eventually became understood as the amplitude for a string-like object vibrating in space. This unexpected mathematical structure led researchers to consider whether the strong force could be modeled by vibrating strings. However, this early version of string theory, now known as bosonic string theory, had several issues. It predicted only bosons, particles that carry forces, but no fermions, which make up matter. More problematically, it required a universe with 25 spatial dimensions plus one of time to be mathematically consistent. It also contained a particle with imaginary mass, known as a tachyon, suggesting an instability in the theory. Despite these problems, bosonic string theory laid the groundwork for later developments. One of the crucial breakthroughs came with the discovery that string theory naturally includes a massless spin-2 particle in its spectrum. Such a particle is exactly what is expected for the graviton, the hypothetical quantum particle that would mediate the force of gravity. This result provided the first hint that string theory might be much more than a theory of the strong force. It could, in principle, provide a quantum theory of gravity, something that had eluded physicists for decades. Mathematically, string theory requires a careful balance to avoid inconsistencies. One such inconsistency is known as an anomaly, where a symmetry present in the classical version of a theory disappears after quantization. Anomalies often lead to physical contradictions, such as the violation of conservation laws. The breakthrough came when physicists Michael Green and John Schwartz demonstrated that certain anomalies in string theory cancel out, but only under very specific conditions. Their 1984 result, known as anomaly cancellation, revitalized interest in string theory and launched what is often referred to as the first superstring revolution. This event marked a turning point, transforming string theory from a mathematical curiosity into a serious candidate for a unified theory of all fundamental interactions. The consistency of the theory relies on the careful interaction of its components, including conformal symmetry on the world sheet, the two-dimensional surface traced by a moving string, modular invariance, and the requirement for strings to propagate in a fixed number of dimensions for mathematical self-consistency. An essential distinction between string theory and earlier quantum field theories lies in its treatment of interactions. In quantum field theory, particle interactions are represented by Feynman diagrams, with point-like vertices where particles collide. In string theory, interactions occur by the splitting and joining of strings, processes that are smooth and continuous. This difference eliminates the ultraviolet divergences that arise when particles interact at a single point in space, a major problem in attempts to quantize gravity using traditional field theory. Another profound implication of string theory is that it unifies what would otherwise be separate fields into a single framework. In quantum field theory, each particle is associated with a distinct field, an electron field, a photon field, and so on. In string theory, a single object, the string, gives rise to all these particles through its vibrational modes. The framework implies that what we perceive as different particles are in fact just different resonances of a more fundamental entity. While string theory provides elegant solutions to many long-standing problems in physics, it introduces its own set of challenges. One of the most significant is the lack of experimental access. The characteristic length scale of strings is far smaller than anything we can currently probe, many orders of magnitude smaller than the distances explored by the most powerful particle accelerators. This makes direct detection of string behavior currently impossible. Additionally, string theory is highly sensitive to the shape and topology of the extra dimensions it postulates. Different compactifications of these dimensions yield different low-energy physics, which means that string theory can, in principle, accommodate a vast number of possible physical universes, each with different particles and forces. This leads to what is known as the string landscape, a term describing the multitude of possible vacuum states allowed by the theory. Despite these difficulties, string theory continues to provide useful insights. Its mathematical structure has influenced other areas of theoretical physics, including black hole entropy calculations, dualities between seemingly unrelated theories, and the development of tools in quantum field theory itself. Even outside physics, string theory has found surprising applications in pure mathematics, leading to progress in fields such as algebraic geometry and topology. It is important to acknowledge that while string theory is rich, elegant, and internally consistent, it is not yet a proven description of nature. Many of its predictions lie beyond current experimental capabilities, and some of its foundational assumptions, such as the existence of strings themselves, remain theoretical. As such, string theory exists at the boundary between mathematical exploration and physical explanation. Nevertheless, it occupies a unique place in modern theoretical physics. It is one of the few frameworks that successfully incorporates gravity into a quantum context. Its internal logic appears consistent, and it has passed numerous theoretical consistency checks. Even if it turns out not to be the final theory of nature, it may still be a vital step toward one. And while string theory may not yet give us definitive answers, it provides a radically new lens through which to examine the universe. A lens where the fundamental building blocks of nature are not dots, but vibrating threads. A lens where space and time might not be what they seem. Perhaps we are still at the beginning of understanding the true geometry of reality, and string theory is merely our first glimpse. It is not unusual in science for the most powerful ideas to arise before the tools exist to test them. If string theory turns out to be true, it will not just describe particles. It will describe the framework that particles emerge from. And in doing so, it may teach us that what we thought of as solid, indivisible pieces of reality were never fundamental at all. Just different notes played on the same vibrating string. Chapter 2. The need for a unified theory. Modern physics is built on two extraordinarily successful, yet fundamentally different frameworks: quantum field theory and general relativity. Each describes a domain of nature with exceptional precision. Quantum field theory governs the behavior of subatomic particles and their interactions, while general relativity governs gravity and the structure of space-time. Despite their success, the two theories are mathematically incompatible at a fundamental level. This inconsistency becomes most apparent under extreme conditions, such as those near black holes or in the earliest moments of the universe, where both quantum effects and gravity are significant. Quantum field theory describes matter and the three non-gravitational forces through a probabilistic framework. Particles are modeled not as discrete, isolated objects, but as excitations in underlying quantum fields. This approach, developed throughout the 20th century, culminated in the Standard Model of particle physics, a theory that has withstood every experimental test to date. It accurately predicts the behavior of electrons, neutrinos, quarks, and force-carrying particles like photons, gluons, and W and Z bosons. However, gravity is conspicuously absent from this model. General relativity, by contrast, is a classical field theory. It models gravity not as a force transmitted by a particle, but as the curvature of spacetime caused by mass and energy. It has passed every empirical test in the macroscopic domain, from the precession of Mercury's orbit to the bending of starlight around massive objects, from gravitational lensing to the recent detection of gravitational waves. General relativity explains the large-scale structure of the cosmos, including black holes, cosmological expansion, and the geometry of the universe itself. Yet these two pillars of physics cannot be reconciled under the same mathematical umbrella. The fundamental conflict arises from their differing assumptions about space, time, and measurement. In quantum mechanics, uncertainty is inherent. Particles do not have definite positions or velocities until measured. General relativity, on the other hand, treats space-time as a smooth, continuous manifold, with positions and trajectories defined deterministically by the curvature caused by mass and energy. When we attempt to apply the principles of quantum mechanics to the gravitational field, the result is a breakdown in mathematical consistency. The infinities that arise in such calculations cannot be absorbed or renormalized in the way they can in quantum electrodynamics or other gauge theories. This incompatibility becomes critical when studying environments where both quantum and gravitational effects are strong. For example, in the center of a black hole, or at the origin of the universe, the Big Bang, both quantum uncertainty and gravitational curvature dominate. In these settings, neither quantum field theory nor general relativity alone can provide a coherent description. What is needed is a framework that unites the probabilistic nature of quantum theory with the geometric treatment of gravity. Physicists have long pursued such a unification. Historically, the desire to unify the forces of nature has been a driving motivation in theoretical physics. James Clerk Maxwell successfully unified electricity and magnetism in the 19th century into a single electromagnetic force. Later, the electromagnetic and weak nuclear forces were combined into the electroweak theory. These successes inspired hope that a similar unification could encompass all four known forces: electromagnetic, weak, strong, and gravitational. Efforts to incorporate gravity into this unifying framework, however, have proven far more difficult. One reason is that gravity is vastly weaker than the other forces at ordinary energy scales. In fact, it is so weak that its effects are essentially negligible when studying subatomic particles. Yet it dominates at large scales, shaping the orbits of planets, stars, and galaxies. This difference in strength means that any unified theory must explain not only how gravity works in the quantum regime, but also why it is so weak relative to the other interactions. Several approaches have been attempted. One idea is to quantize gravity in the same way the electromagnetic field is quantized in quantum electrodynamics. This leads to a hypothetical particle called the graviton, a massless spin-2 particle that would mediate gravitational interactions. However, when calculations are performed in this framework, they quickly become unmanageable. The theory produces infinities that cannot be eliminated through standard techniques, making it non-renormalizable. Another approach is known as loop quantum gravity, which attempts to quantize spacetime itself using discrete loops of geometry. While promising in certain areas, it has not yet succeeded in producing a complete theory that includes all other forces. Other models, such as asymptotic safety and causal dynamical triangulations, offer additional insights but remain limited in scope. This is where string theory enters the picture. It offers a radically different starting point by discarding the idea that fundamental entities are zero-dimensional points. Instead, it proposes that all particles are different vibrational modes of one-dimensional strings. This change in assumption has profound consequences. One of the most important is that string theory naturally includes a graviton in its spectrum. Unlike ad hoc attempts to insert gravity into a quantum framework, string theory predicts gravity as a necessary outcome. Moreover, string theory provides a consistent way to unify all known forces under a single mathematical structure. It does so by extending the concept of gauge symmetry and embedding it into a higher dimensional spacetime. This structure allows string theory to potentially encompass the Standard Model, general relativity, and their interactions. While these connections are still being worked out in detail, the overall coherence of the theory is unmatched by any other approach. A key feature of any unified theory is that it must reduce to known physics in the appropriate limits. String theory appears capable of reproducing both general relativity and quantum field theory when energies are low compared to the string scale. This suggests it might serve as a more fundamental framework from which both current theories emerge as approximations. Another benefit of unification is explanatory power. Instead of treating the dozens of particles and parameters in the Standard Model as unrelated inputs, a unified theory could explain why they exist, why they have the masses and charges they do, and how they interact. In such a framework, complexity arises from the underlying structure of the theory, not from arbitrary choices. Still, challenges remain. One of the most pressing is the lack of direct experimental evidence for any candidate unified theory, including string theory. The predicted phenomena often occur at energy scales far beyond current technological capabilities. This makes empirical validation difficult, though not impossible. Some researchers hope that indirect evidence, such as the discovery of supersymmetric particles or specific patterns in the cosmic microwave background, might provide support for these theories. Another issue is uniqueness. A successful theory of everything must not only be internally consistent and empirically accurate, but it must also be unique. Currently, string theory allows for a vast number of possible solutions, corresponding to different ways the extra dimensions can be compactified. This so-called landscape problem raises the question of whether the theory is too flexible to make precise predictions. Despite these uncertainties, the drive toward unification remains strong. It is motivated not just by practical concerns, but by a belief in the underlying order of the universe. The success of earlier unification efforts suggests that the forces of nature may not be fundamentally separate. They may instead be manifestations of a deeper symmetry, hidden at everyday energies, but revealed at the most fundamental levels of reality. Some critics argue that the search for unification is driven more by aesthetic preferences than empirical necessity. Yet history shows that mathematical elegance often points the way to physical truth. The equations of general relativity, for example, were derived from symmetry principles and geometric reasoning before they were confirmed by experiment. Likewise, the Standard Model was constructed to preserve gauge invariance long before many of its predictions were verified. In the end, the need for a unified theory is both practical and philosophical. Practically, it is required to resolve the inconsistencies that arise when gravity and quantum mechanics are both significant. Philosophically, it reflects a desire to see nature as a coherent whole, to find a single framework that explains the behavior of all matter and energy across all scales. And perhaps, beyond the mathematics and experimental hurdles, lies something more human, the need to understand the structure of the world not just in fragments, but as a complete system. The unified theory would not only describe how things work, it would reveal why the laws of physics are the way they are. Even if the journey remains incomplete, the pursuit itself brings us closer to understanding the foundations of reality. Chapter 3. How strings replace particles. In traditional physics, elementary particles are treated as point-like objects with no spatial extent. This abstraction works remarkably well within quantum field theory, where particles are represented as excitations of their respective fields, localized to a single point in space. However, this point-particle model comes with inherent limitations, especially when extended to high-energy interactions or attempts to quantize gravity. String theory proposes a fundamentally different approach. Instead of treating particles as zero-dimensional points, it models them as one-dimensional objects, strings, whose vibrational patterns determine the particle's identity and properties. This shift in representation from points to strings is not merely a mathematical curiosity. It changes the way we understand the structure of matter and the nature of the interactions that govern it. A single string can vibrate in multiple ways, and each distinct vibrational state corresponds to a different particle. The various characteristics that distinguish one particle from another, such as mass, charge, and spin, are no longer intrinsic features of individual point-like entities, but rather emerge from the string's mode of vibration. One of the most compelling aspects of this formulation is its unifying power. Whereas in the Standard Model, different particles are associated with different quantum fields, string theory proposes that all particles, regardless of type, arise from the same kind of fundamental object. There are not dozens of fundamentally different particles, but rather a single type of string manifesting differently depending on its vibrational energy and spatial configuration. To understand how this replacement works, we must begin with the basic mechanics of a string. Strings can be open with two distinct endpoints, or closed, forming a loop. As they move through space, they trace out two-dimensional surfaces called world sheets, analogous to how a point particle traces out a one-dimensional world line. The physics of these strings is governed by equations that describe how they move, how they interact, and how they vibrate. The spectrum of solutions to these equations determines the particle content of the theory. Different vibrational modes produce different energy levels, and through the equivalence of energy and mass, this translates into a spectrum of particle masses. One vibrational mode might correspond to a massless particle like the photon, another to a massive particle like the W boson. Crucially, one of the modes corresponds to a massless spin-2 particle, which is identified as the graviton, the quantum carrier of gravity. This result does not require additional assumptions or insertions. It emerges naturally from the mathematics of string theory, offering a potential path to a quantum theory of gravity. This elegant mechanism, where all particles are just string states, brings several advantages. First, it provides a unified description of both matter and force-carrying particles. Second, it eliminates many of the infinities that arise when point particles interact at a single location in spacetime. Because strings have a finite size, their interactions are spread out over a small region, smoothing out the ultra-short distance behavior that typically leads to divergence in quantum field theory. This regularization is built into the theory and does not rely on additional adjustments or renormalization tricks. The replacement of point particles with strings also changes the way interactions are visualized. In quantum field theory, particles interact by exchanging virtual particles at interaction vertices in Feynman diagrams. These diagrams include sharp points where lines intersect, an abstraction that becomes problematic at very high energies. In string theory, interactions are smoother processes in which strings split and rejoin. The corresponding diagrams have no sharp points. Instead, they feature continuous surfaces where strings merge or separate. This structure leads to better high-energy behavior and mathematical consistency. String theory's ability to reproduce the known features of particles also depends on its incorporation of internal symmetries. Different vibrational states correspond not just to differences in energy, but also to different quantum numbers. Properties like electric charge or color charge. These arise from how strings wind or oscillate in compactified dimensions, a feature that will be explored more deeply in later chapters. For now, it's enough to note that the way strings behave in additional spatial dimensions influences their properties in observable four-dimensional spacetime. The mathematics behind this is highly non-trivial. The vibrational patterns of strings are described by quantized solutions to equations that depend on the geometry of the space in which the string resides. The consistency of these solutions requires that strings move in more than 3 spatial dimensions. Specifically, different versions of string theory require different total dimensionalities. Some call for 10, others for 11. These additional dimensions are not visible in everyday life because they are compactified or curled up at scales far smaller than those we can observe directly. Despite its elegance, the idea of replacing particles with strings is not without challenges. One issue is that string theory, as currently understood, predicts a vast number of possible vibrational modes and resulting particles, many more than are observed in nature. This includes hypothetical particles that may exist only at very high energies or in early universe conditions. While some of these states may correspond to particles we haven't yet discovered, others might never appear in our physical universe. Moreover, string theory is still a work in progress. The full set of equations governing the theory has not been solved in general. Many results are known only in specific regimes or approximations. Much of the work in string theory involves exploring different backgrounds, specific ways in which the extra dimensions can be compactified and strings can move. Each background leads to a different set of low-energy physical predictions, raising the question of why our universe appears to have the properties it does. In addition, experimental confirmation remains elusive. The typical energy scale at which string-like behavior would become apparent is thought to be near the Planck scale, far beyond the reach of current or near-future particle accelerators. This makes direct tests of the theory extremely challenging. Indirect signals, such as subtle deviations in particle behavior or cosmological patterns, are being sought, but so far, no definitive evidence has been found that would confirm the existence of fundamental strings. It's also worth noting that while string theory replaces particles with one-dimensional objects, it also introduces higher-dimensional objects known as branes. These play a role in how strings interact and how the universe may be structured on larger scales. While brains are not the focus of this chapter, they become important when considering how different vibrational modes are constrained or allowed to interact with the dimensions in which they propagate. A further refinement in understanding how strings give rise to particles lies in the distinction between open and closed strings. Open strings have two endpoints, while closed strings form loops with no endpoints. This difference has meaningful implications in how various particles arise. In many formulations of string theory, open strings give rise to particles that include force carriers associated with electromagnetism, the weak force, and the strong force. In contrast, closed strings inherently produce particles that are not confined to localized interactions. Most notably, the graviton is always associated with a closed string mode. This division leads to important structural consequences. Open strings are often attached to higher dimensional objects called D-branes, which restrict the directions in which the string can vibrate or move. The properties of the resulting particles depend in part on how the endpoints of the strings are constrained, an aspect determined by the boundary conditions imposed on the strings. These boundary conditions define how the string behaves at its endpoints, influencing which vibrational modes are allowed, and thus which particles can emerge. In technical terms, these boundary conditions can be of Newman type, allowing endpoints to move freely, or Dirichlet type, where endpoints are fixed. In physical terms, the former leads to particles that can move through the brain, while the latter confines them to specific dimensions. This concept is fundamental when attempting to model our observed four-dimensional world within a higher dimensional framework. Certain string modes may be restricted to our visible universe, while others might extend into hidden dimensions, providing a theoretical explanation for why we observe only a subset of possible particle behaviors. The physical properties of these string vibrations also depend on the string's tension, a measure of how much energy is required to stretch the string. A string under higher tension resists distortion more strongly and has different vibrational spectra compared to a string under lower tension. This parameter plays a role in determining the mass and energy of the resulting particles. In practice, the tension is often associated with the characteristic scale of the theory. It sets the energy level at which stringy effects become significant, and at lower energies, the vibrational modes reduce to particle-like behavior that closely resembles the predictions of quantum field theory. These oscillation modes include both longitudinal and transverse vibrations, and the mathematical treatment involves decomposing the string's motion into harmonic modes. Each of these contributes to the total energy of the state, and by extension, to the mass of the corresponding particle. This structured and quantized spectrum of vibrations leads to a layered pattern of possible particles, some of which match known physics, and others which remain theoretical. The interpretation of these vibrational modes can be formalized using tools like conformal field theory, which describes how fields behave on the two-dimensional surface traced out by the string. This surface, called the world sheet, acts as a canvas on which the dynamics of the string unfold. The requirement that the theory be conformally invariant at the quantum level leads to deep constraints on the number of dimensions in which the string can consistently propagate. These requirements are not arbitrary. They arise from the need to eliminate anomalies and inconsistencies in the quantum behavior of the string. Altogether, the process of replacing particles with strings does more than shift the basic unit of matter. It introduces a fundamentally new ontology for physics. Instead of a universe composed of isolated points interacting through mysterious forces, string theory paints a picture of connectedness. Each interaction is not a sudden, discontinuous event, but a continuous transformation of extended objects. The complexity of particle behavior becomes the reflection of a deeper geometrical and dynamical structure. While this approach remains beyond our current experimental reach, its internal consistency and far-reaching implications continue to make it one of the most studied and developed areas in theoretical physics. The mathematical richness of string theory and its ability to reproduce many known features of particle physics support its ongoing relevance. Whether string theory is ultimately the correct description of nature remains unknown. But the notion that particles are not objects in themselves, but rather manifestations of a deeper underlying entity, strings, has already influenced how physicists think about the structure of reality. It provides a compelling, though still unconfirmed narrative that suggests simplicity at the heart of the apparent complexity of matter. And if this is true, if the essence of reality is vibration, not substance, then perhaps everything we see is just a pattern woven from something deeper and more fundamental than form. A note in a silent song, echoing across the invisible dimensions of a universe still being tuned. Chapter 4. Extra Dimensions in String Theory. One of the most surprising and non-intuitive predictions of string theory is that the universe consists of more than the familiar 3 dimensions of space and 1 of time. In order to maintain internal mathematical consistency, string theory requires additional spatial dimensions, dimensions that are hidden from direct observation. These extra dimensions are not an optional feature, but a foundational requirement of the theory itself. The necessity for extra dimensions arises from the demand that string vibrations behave in a way that preserves a critical symmetry called conformal invariance. When a string propagates through space, it sweeps out a 2-dimensional surface called a world sheet. The physics on this world sheet must remain invariant under certain mathematical transformations, or else inconsistencies, such as anomalies and non-physical predictions, arise. Calculations show that in order to preserve these symmetries at the quantum level, the total number of spacetime dimensions must exceed 4. Different versions of string theory require different dimensional frameworks. The simplest version, bosonic string theory, requires 26 spacetime dimensions. However, this version suffers from the presence of unphysical features like tachyons and the absence of fermions. More realistic versions of string theory, such as superstring theories, require 10 dimensions, 9 of space and 1 of time. When extended further into frameworks like M-theory, which attempts to unify all superstring theories into a single overarching structure, the required number of dimensions increases to 11. The fact that we observe only 3 dimensions of space raises an important question. If these extra dimensions are real, why don't we see them? The prevailing explanation involves a process known as compactification. This is the idea that while 3 spatial dimensions extend infinitely in all directions, the additional dimensions are compacted or curled up at extremely small scales. They form closed geometric shapes that are so tiny, far smaller than the scale accessible by current experiments, that their presence cannot be detected directly. To visualize this, consider a common analogy: a garden hose. From a distance, the hose looks like a one-dimensional line, but upon closer inspection, one sees that it has a circular cross-section. It possesses a second dimension wrapped around itself. Similarly, in string theory, each point in ordinary space may include tiny, compact dimensions shaped in complex geometries. The mathematical structures used to describe these compactified dimensions are known as Calabi-Yau manifolds. These are complex, multidimensional shapes that satisfy specific requirements for curvature and symmetry, allowing them to preserve the supersymmetry necessary for string theory's consistency. A Calabi-Yau space typically has 6 dimensions, which, combined with the 4 dimensions of spacetime we observe, yields the 10 dimensions required by superstring theory. The shape and topology of these compactified dimensions are not mere mathematical curiosities. They have physical consequences. The way strings vibrate is influenced by the geometry of the space in which they move. Different Calabi-Yau shapes result in different vibrational modes, which in turn determine the properties of the particles that emerge from those strings. The masses, charges, and interactions of particles depend on the specific structure of the compact dimensions. Thus, the details of these hidden spaces may account for the diversity of particles in the standard model. One major implication of this is that string theory does not predict a single, unique universe. Instead, there exists a vast number of possible Calabi-Yau configurations, each corresponding to a different version of low-energy physics. This leads to what is known as the string landscape, a massive collection of possible solutions to the equations of string theory. Each point in this landscape represents a consistent universe with its own physical laws, particle content, and constants of nature. The existence of this landscape has sparked both excitement and controversy. On one hand, it suggests that string theory is flexible enough to encompass the vast complexity of physical phenomena observed in our universe. On the other, it raises the concern that the theory may be too flexible. If anything can be described by some configuration of compact dimensions, how can we determine which version corresponds to our world? This is known as the problem of predictivity. To address this, physicists explore mechanisms that might select one vacuum configuration from among many. Some approaches involve dynamical processes during the early universe, such as cosmic inflation, which might funnel physical reality into specific regions of the landscape. Others invoke the anthropic principle, suggesting that only those universes compatible with the emergence of complex structures and life will be observed at all. Despite these conceptual challenges, the idea of extra dimensions provides a natural framework to unify the various forces and particles of nature. For example, higher dimensional theories allow for unified gauge symmetries that, when broken by the geometry of the compact dimensions, yield the observed separation of forces. In such scenarios, gravity and the other interactions all originate from a common higher dimensional source, with their apparent differences resulting from how they manifest in a lower dimensional projection. In addition to influencing particle physics, extra dimensions have implications for cosmology. Certain models suggest that our universe may be a three-dimensional brain embedded within a higher dimensional bulk space. In these brain-world scenarios, particles and forces associated with the standard model are confined to the brain, while gravity is free to propagate into the extra dimensions. This could potentially explain why gravity appears so much weaker than the other forces. It is diluted across the extra dimensions, while the others remain confined. Such models also predict potential signatures that could, in principle, be observed. For instance, the existence of large or warped extra dimensions could alter the behavior of gravity at very short distances. Experiments have been conducted to test for deviations from Newton's law of gravity at millimeter and sub-millimeter scales, though no anomalies have been detected so far. Other possible signals include missing energy events at high-energy particle colliders or subtle patterns in cosmic microwave background radiation, though these remain speculative. One of the major difficulties in confirming the existence of extra dimensions lies in their extremely small size. If the compactification scale is near the Planck length, current experimental technologies are orders of magnitude too crude to probe them directly. Nevertheless, the mathematical consistency and unifying potential of higher dimensions remain a powerful motivation for continuing research. Another area of investigation is the stability of compactification. Not all configurations of extra dimensions are dynamically stable. Some may collapse or expand over time, altering the observable laws of physics. Understanding what stabilizes these dimensions often referred to as moduli stabilization, is an ongoing challenge. Various mechanisms involving fluxes, branes, or quantum effects have been proposed, but no universally accepted solution has emerged. Furthermore, the geometry of the extra dimensions can influence not just particle properties, but also cosmological parameters such as the cosmological constant. Certain compactification schemes may provide a natural way to generate small positive vacuum energy, consistent with the observed accelerated expansion of the universe. Others may offer insights into the initial conditions of the cosmos or the origin of cosmic inflation. While the idea of extra dimensions is deeply mathematical, it connects directly to physical observables in a variety of subtle ways. Every successful model of string compactification must reproduce the known physics of our universe: the correct particle spectrum, the appropriate symmetry breakings, and the observed constants of nature. This is a high bar, and only a small subset of possible compactification scenarios appear compatible with current data. Yet, even this narrow subset contains an enormous variety of models, each with potentially different consequences. This richness has encouraged the development of new computational tools, databases of Calabi-Yau manifolds, and machine learning methods to explore the landscape efficiently. The interplay between geometry and physics is perhaps nowhere more evident than in this area of string theory, where abstract shapes can dictate the rules of matter and force. And still, fundamental questions remain unanswered. Are these extra dimensions real physical entities or merely useful mathematical constructs? Is there a principle yet undiscovered that selects one compactification over all others? Could future observations reveal indirect hints of extra-dimensional influence, or will they remain hidden forever behind the limits of measurement? While we have no direct sensory access to these hidden dimensions, their implications resonate through every corner of string theory. They provide the backdrop against which the vibrations of strings define the particles of nature. They explain why forces appear distinct, why constants have the values they do, and why matter behaves in certain structured ways. In a sense, the unseen shapes of these dimensions silently sculpt the laws of the universe. And perhaps at the very edge of what can be known lies the idea that our reality is only a shadow cast from a higher dimensional world, one where the depth and geometry of space reach far beyond anything we have ever seen, not just around us, but within every point, compact and quiet, yet responsible for the very fabric of what we call real. Chapter 5. Supersymmetry and Superstrings. Supersymmetry, often abbreviated as SUSI, is a theoretical symmetry that postulates a deep relationship between the two fundamental classes of particles in nature, bosons and fermions. Bosons are particles that mediate forces, such as photons and gluons, while fermions are the constituents of matter, such as electrons and quarks. In supersymmetric theories, every boson has a corresponding fermionic partner, and every fermion has a corresponding bosonic partner. This pairing is not observed in current experimental data, but it forms the basis for extending the standard model and constructing viable versions of string theory known as superstring theories. The concept of supersymmetry arose independently of string theory. It was initially developed within quantum field theory as a possible solution to several theoretical problems. One of the key motivations was to address the so-called hierarchy problem, which concerns the vast difference in strength between the gravitational force and the other fundamental forces, particularly the electroweak interaction. Supersymmetry helps to stabilize the Higgs boson mass against large quantum corrections, which would otherwise drive it to unnaturally high values. By introducing superpartners that cancel out these corrections, supersymmetry offers a mechanism to preserve the relative scales of the fundamental forces. In addition to its stabilizing effects, Supersymmetry improves the mathematical behavior of quantum field theories. It allows for more controlled high-energy behavior, reducing divergences that typically plague loop-level calculations. This makes theories more predictive and manageable and allows for better unification of coupling constants at high energies, something not easily achieved in the standard model without supersymmetric extensions. In the context of string theory, supersymmetry plays an even more central role. The earliest versions of string theory, such as bosonic string theory, suffered from several theoretical deficiencies. These included the existence of tachyons, hypothetical particles with imaginary mass that signal an instability in the vacuum, and the complete absence of fermions in the particle spectrum. Supersymmetry offered a way to address both issues. By extending the symmetry of the string's vibrations to include transformations between bosonic and fermionic modes, a more consistent version of the theory emerged. The resulting framework is known as superstring theory. It incorporates supersymmetry at the level of the string worldsheet and allows for the inclusion of both bosons and fermions in the physical spectrum. The presence of supersymmetry removes tachyons from the theory and ensures that the quantum anomalies, which could otherwise render the theory inconsistent, cancel out. These cancellations are not optional. They are required for the internal consistency of the theory. In fact, anomaly cancellation was one of the key insights that revived interest in string theory during the 1980s, marking the beginning of the so-called first superstring revolution. Superstring theory differs from bosonic string theory in several significant ways. First, it requires 10 spacetime dimensions rather than 26. This reduction comes from the additional structure introduced by supersymmetry, which places tighter constraints on the theory's consistency. Second, it naturally includes both types of particles found in nature, matter and force carriers, emerging from a unified framework. Third, superstring theories can describe a wider range of interactions and more complex geometrical configurations, including various types of branes and dualities. There are 5 known consistent superstring theories. These are not arbitrarily defined but are derived from rigorous mathematical constraints. They are known as Type 1, Type 2a, Type 2b, and the 2 heterotic theories, heterotic SO32 and heterotic E8 Tice E8. Each has its own characteristics, including the types of strings it permits, open, closed, or both, the presence or absence of certain symmetries, and the way supersymmetry is implemented in 10 dimensions. Despite their differences, these 5 theories are deeply interconnected, as later chapters will explore. Supersymmetry in superstring theory is not merely an added feature, it is a structural necessity. Without it, the theory breaks down. Supersymmetry allows for the elegant unification of gravity with the other forces, as the graviton appears naturally in the spectrum of closed string vibrations, while other vibrational modes correspond to known gauge bosons and their fermionic partners. This unification is not manually inserted, it is embedded in the theory's construction. Despite its mathematical elegance, supersymmetry faces significant challenges from an empirical standpoint. If superpartners exist for every known particle, why haven't we observed them? This question has grown more pressing in recent years as experiments at high-energy colliders such as the Large Hadron Collider have failed to detect any evidence for supersymmetric particles. These null results have forced physicists to reevaluate the parameter space of supersymmetric models. One possibility is that supersymmetry is a broken symmetry in nature, meaning the superpartners exist but have masses too large to be currently detectable. This idea is consistent with theoretical models that allow for spontaneous symmetry breaking, much like what occurs in the standard model with electroweak symmetry. In string theory, supersymmetry breaking can occur through several mechanisms, many of which are related to the geometry and topology of the extra dimensions. The compactification process that hides additional spatial dimensions may also break supersymmetry, either partially or completely, depending on the specific features of the compact space. This leads to a variety of low-energy effective theories, some of which resemble known physics and others that diverge from it significantly. Another aspect of supersymmetry in string theory is its connection to dualities. Supersymmetric string theories exhibit a wide range of dualities, mathematical transformations that relate seemingly different theories or regimes. These dualities suggest that the 5 superstring theories are not fundamentally distinct, but are instead different manifestations of a single underlying framework. Supersymmetry is a crucial ingredient in establishing these dualities, as it preserves the mathematical consistency needed for them to hold. Beyond its role in theoretical physics, supersymmetry has also influenced developments in pure mathematics. It has led to insights in algebraic geometry, topology, and the study of moduli spaces. Mathematical structures arising from supersymmetric field theories have inspired new theorems and conjectures in fields that were once considered far removed from high-energy physics. This cross-disciplinary impact underscores the richness of the symmetry principle and its relevance beyond particle physics. However, the very richness of supersymmetric models also presents a challenge. There are many different ways to implement supersymmetry, and the lack of empirical data makes it difficult to narrow down which version, if any, corresponds to our universe. The vast number of possible supersymmetric extensions of the standard model and their embedding in string theory adds to the difficulty of making concrete, testable predictions. At a mathematical level, supersymmetry is represented by an extension of the space-time symmetry algebra known as the super-Poincare algebra. This structure includes not only the generators of translations and Lorentz transformations, as in ordinary relativistic quantum field theory, but also new fermionic generators called supercharges. These operators transform bosons into fermions and vice versa, and they obey specific anti-commutation relations that distinguish them from the usual bosonic symmetries. One of the remarkable features of supersymmetry algebras is their constrained structure. Only a limited number of supersymmetry generators can exist in a consistent relativistic theory in 4 dimensions. Theories with one set of supercharges are referred to as having n equals 1 supersymmetry, while those with more sets are labeled n equals 2, n equals 4, or even higher. Each increase in n adds more structure and symmetry, often leading to greater mathematical control and simplifications in calculations. Extended supersymmetry theories, those with more than one supercharge, are particularly important in theoretical explorations. They tend to be more symmetric, more constrained, and often exactly solvable in certain limits. For instance, n=4 supersymmetric Yang-Mills theory is a highly symmetric gauge theory that is conformally invariant and serves as a valuable testing ground for ideas in both field theory and string theory. Although such theories are too symmetric to describe our universe directly, they provide important laboratories for understanding the deep structure of quantum field theories and dualities. Supersymmetry also helps solve persistent problems in quantum field theory related to divergences. In standard quantum field theories, higher-order corrections often introduce infinities that need to be canceled through a process called renormalization. Supersymmetric theories, however, exhibit improved behavior in this respect. Because superpartners contribute with opposite signs in quantum corrections, many potentially divergent terms cancel out. This cancellation leads to improved ultraviolet behavior and sometimes results in exact results at all orders in perturbation theory. These cancellations are not just theoretical conveniences, they have practical implications. For example, the beta functions that govern the running of coupling constants in supersymmetric theories often vanish or simplify. This feature contributes to the unification of couplings at high energy scales, an important motivation for both supersymmetric extensions of the standard model and for grand unified theories embedded within string theory. In string theory specifically, supersymmetric configurations are often used as starting points for more realistic, non-supersymmetric models. The idea is that by understanding the full structure and stability of supersymmetric solutions, one can then systematically introduce controlled deformations that break supersymmetry in a soft or spontaneous manner. These deformations preserve desirable features like anomaly cancellation, while modifying the spectrum to be more compatible with known physics. The search for supersymmetry also extends to cosmology. Certain inflationary models rely on scalar fields whose potentials are stabilized by supersymmetric mechanisms. Supersymmetry also influences models of dark matter, as the lightest supersymmetric particle is often stable and weakly interacting, making it a natural dark matter candidate. Although no such particle has been detected to date, this possibility continues to guide both theoretical work and experimental searches. The elegance and flexibility of supersymmetry make it one of the most powerful tools in modern theoretical physics. Even if it turns out not to be realized at energy scales accessible to current experiments, its mathematical structure, predictive control, and deep connections to geometry ensure it will remain a central concept in the theoretical landscape. And perhaps, in its vision of a universe where every particle has a hidden twin, where matter and force are not fundamentally different, but merely reflections of each other, supersymmetry whispers something deeper. That nature, at its root, may favor balance not as a constraint, but as a principle of harmony, one that quietly shapes the invisible architecture behind the things we see. Chapter 6: The 5 Superstring Theories. As string theory matured during the late 20th century, physicists discovered something unexpected. Rather than a single, unique theory of superstrings, there appeared to be 5 consistent formulations. Each of these theories satisfied the stringent mathematical demands of anomaly cancellation, supersymmetry, and quantum consistency. Rather than invalidating the idea of string theory, this multiplicity hinted at a deeper unity, one that would eventually lead to the concept of dualities and the proposal of a more fundamental theory encompassing them all. But before reaching that point, it is essential to understand the distinct features that define each of the 5 superstring theories and why they are all mathematically viable frameworks in 10 dimensions. The 5 consistent superstring theories are known as Type 1, Type 2a, Type 2b, heterotic SO32, and heterotic E8x E8. Though they share fundamental principles, like supersymmetry and the requirement of 10 spacetime dimensions, they differ in important structural ways, including the types of strings they allow, the symmetries they preserve, and the kinds of particles they predict. These differences emerge not from arbitrary choices, but from strict mathematical consistency and anomaly cancellation requirements. Type 1 string theory is unique in that it includes both open and closed strings. This is a significant structural choice, as most other superstring theories focus solely on closed strings. In Type 1 theory, the open strings allow endpoints that can move along higher dimensional objects called d-branes, while closed strings propagate freely through the full 10-dimensional spacetime. This theory incorporates a specific gauge group, SO through 2, and its consistency is tightly tied to the cancellation of anomalies, which would otherwise make the quantum theory ill-defined. Type 1 theory is also non-chiral, meaning it treats left-handed and right-handed fermions symmetrically. Type 2a and Type 2b are both theories of closed-oriented strings, but they differ in their handling of spacetime parity. Type 2a string theory is non-chiral. Its left-moving and right-moving modes on the string worldsheet are treated symmetrically. In contrast, Type 2b string theory is chiral. it distinguishes between left and right modes, giving rise to different spectra and interactions. Despite this distinction, both theories are supersymmetric and anomaly-free. Each of them incorporates different types of fields in their low energy limits. Supergravity theories in 10 dimensions, which give them distinct physical characteristics. For example, Type 2a allows for D-branes of even dimensions, while Type 2b allows D-branes of odd dimensions, leading to different configurations for brain dynamics and compactifications. The remaining two string theories are known as heterotic string theories. They are structurally quite different from the types already mentioned, as they combine elements of bosonic string theory with supersymmetric string theory in an asymmetric way. In heterotic theories, the left-moving modes of the string, which determine how it propagates through spacetime, are treated using the supersymmetric formulation, while the right-moving modes use the bosonic string formulation. This hybrid structure is mathematically consistent only under specific conditions, including strict constraints on the allowed gauge groups. Two gauge groups satisfy these requirements: SO32 and E8X-E8. These give rise to two distinct heterotic string theories. Both involve only closed strings and support rich internal symmetries that have made them especially interesting for attempts to model realistic particle physics. In particular, the E8X-E8 heterotic string theory has long been favored in efforts to embed the standard model into string theory, because its gauge group can naturally contain the types of symmetries and particles we observe at low energies. Compactifications of this theory on specific geometric spaces, such as Calabi-Yau manifolds, can result in models with 3 generations of particles, one of the many unsolved puzzles in the standard model. Each of the 5 superstring theories is defined not only by the types of strings it includes and the gauge groups it supports, but also by how it treats supersymmetry. All 5 are 10-dimensional and possess some form of n=1 or n=2 supersymmetry, depending on how many supercharges are present in the theory. Supersymmetry ensures that quantum anomalies cancel and that the physical spectra of the theory are free of unphysical states like tachyons. But it also determines the behavior of the theory when it is compactified to 4 dimensions, a necessary step for relating the 10-dimensional theory to the world we observe. Compactification is the process by which extra dimensions are rendered invisible at low energies. Each of the 5 superstring theories allows for different types of compactification, leading to different effective theories in 4 dimensions. The choice of compactification space affects everything from the number of generations of particles to the strengths of the fundamental forces. In this way, the 5 theories offer a broad landscape of possibilities for constructing viable models of physics, though the vastness of this landscape also contributes to the difficulty of extracting unique, testable predictions. It might seem troubling that 5 theories exist where one might expect only one. However, this multiplicity turned out to be a clue rather than a flaw. During the 1990s, physicists began to discover deep mathematical relationships between the 5 theories. These relationships, called dualities, suggested that the different theories were not truly distinct, but instead described different regimes or limits of a more fundamental underlying theory. For example, under certain conditions, Type 2a and Type 2b string theories can be shown to be mirror images of each other when compactified on specific geometries. Similarly, heterotic SO32 and Type 1 string theory were found to be related by a strong-weak coupling duality, meaning that one theory's strongly interacting regime corresponds to the weakly interacting regime of the other. These dualities do not merely relate similar theories, they relate theories with entirely different spectra, symmetries, and dimensional objects. This unification of the five string theories under duality transformations led to the realization that all five might be facets of a single, more encompassing framework, later called M-theory. Though M-theory itself is still poorly understood and not yet fully formulated, it represents the hope that the multiplicity of superstring theories is a feature of a deeper unity. From a practical standpoint, the five superstring theories provide a rich toolkit for building theoretical models. Each can be compactified in a multitude of ways, and each leads to a different set of low-energy predictions. This variety is both a strength and a challenge. On one hand, it allows for flexibility in constructing models that resemble known physics. On the other, it leads to what has been called the landscape problem: the existence of a vast number of possible vacua or configurations, many of which are mathematically valid but physically indistinct. This issue complicates the task of making precise predictions and is one reason why string theory has sometimes been criticized as being difficult to test. The richness of the five superstring theories also gave rise to new mathematical objects that play crucial roles in how strings interact and organize. Among these are D-branes, short for Dirichlet branes, which are hypersurfaces on which open strings can end. These objects are not secondary elements, but rather integral components of the theory. Depending on the string theory in question, D-branes can have various dimensionalities and dynamical behaviors, and their inclusion deepens the connection between geometry and physics. In type 1 string theory, for instance, open strings must end on D9 branes that fill the entire spacetime, whereas type 2a and 2b allow for branes of different dimensions. These branes give rise to gauge fields, massless excitations, and even non-perturbative phenomena that cannot be described using traditional methods. The different theories also govern the kinds of solitonic objects, localized, stable field configurations they allow. These include not just strings and branes, but also black brane solutions and exotic higher dimensional analogs. Each string theory admits its own set of such configurations, and many of them are mapped onto each other under the known dualities. The presence of these objects suggests that string theory is not merely a theory of one-dimensional strings, but a broader framework that includes extended objects of various dimensionalities, all governed by consistent quantum rules. Another point of divergence among the five theories is how they treat orientability. Type 1 string theory, for instance, includes unoriented strings, ones in which the direction along the string is not meaningful, while the other theories rely on oriented strings. This difference influences the symmetries present in the theory and the types of interactions that are permitted. Moreover, the way each theory handles modular invariance, the requirement that certain transformations on the string world sheet do not alter physical predictions, also helps classify their behavior and restrict the allowed spectrum of particles. From a low-energy perspective, each of the five superstring theories reduces to a different kind of 10-dimensional supergravity theory, reflecting the underlying symmetry and field content of the parent string theory. These supergravity theories serve as classical approximations and are used extensively in model building, cosmological applications, and studies of black holes. Although supergravity itself is not expected to be a complete theory, it provides a bridge between full string theory and familiar four-dimensional physics. The dualities connecting the five theories, such as S-duality, T-duality, and U-duality, are not just clever mathematical tricks. They reveal something profound about how different physical regimes are connected. S-duality, for example, relates strongly coupled behavior in one theory to weakly coupled behavior in another. T-duality connects large compactification radii with small ones, suggesting that spacetime itself may have a kind of built-in redundancy. These ideas challenge classical notions of scale, geometry, and locality, indicating that the universe at fundamental scales may not behave according to familiar intuitions. Understanding these relationships has also helped researchers explore the string landscape, the vast collection of possible string vacua. Each vacuum represents a different solution to the equations of string theory, characterized by a particular compactification manifold, brane configuration, and field content. While this landscape may contain solutions compatible with known physics, it also contains an enormous number of others that do not. Navigating this landscape and identifying potentially realistic vacua remains one of the great challenges in string theory today. As research continues, the role of the 5 superstring theories has shifted from being seen as competing models to components of a greater whole. This change in perspective reflects a more general trend in theoretical physics, the realization that apparently distinct systems can be unified under deeper principles. Though these 5 theories emerged from different starting points, their underlying structures suggest that they are simply different windows onto the same underlying reality. Each of these theories can be studied in isolation, with its own mathematical tools and physical interpretations, but their interconnections hint at something more fundamental. Whether that something is M-theory, a holographic framework, or a still undiscovered principle, the story of the 5 superstring theories continues to shape our understanding of the deep architecture of nature. And perhaps as we glimpse these 5 reflections of a deeper symmetry, we are witnessing a quiet truth, that the universe may not present its secrets all at once, but through shifting facets, each revealing a sliver of something whole, each inviting us to look deeper. In this patchwork of string theories, there may lie not contradiction, but invitation, the kind that beckons us to explore until the illusion of difference fades into unity. Chapter 7: Dualities and the Unification of String Theories. As physicists explored the 5 superstring theories, they were confronted with a peculiar paradox. Each theory was self-consistent and mathematically valid. Each operated in 10 dimensions, incorporated supersymmetry, and avoided anomalies, yet none appeared uniquely superior. Were these theories different expressions of an underlying truth, or was string theory as a framework inherently fragmented? This puzzle began to unravel in the 1990s with the discovery of dualities, precise mathematical correspondences that relate seemingly different physical theories. Dualities do not merely connect abstract formulas. They reveal that one theory, under certain conditions, becomes indistinguishable from another theory operating in a different regime. Strong interactions in one framework can map to weak interactions in another. A large space in one theory might be equivalent to a tiny one in another. These insights suggested that the 5 string theories were not truly separate, but rather different perspectives on the same fundamental structure. The first major duality explored was T-duality. It arises in theories with compactified dimensions, spaces that loop back on themselves like a circle. Imagine a string propagating in a universe where one spatial dimension is curled into a circle. The string can move around the circle, but it can also vibrate in specific modes determined by the circle's size. It turns out that a string compactified on a circle of radius r behaves identically to a string on a circle of radius inversely proportional to r. In other words, a very large compact dimension is physically equivalent to a very small one. This symmetry is not just an approximation, it holds exactly in certain string theories, like type 2a and type 2b. T-duality interchanges the vibrational and winding modes of the string and shows that spatial scale is not an absolute notion at the quantum level. The implications of T-duality are far-reaching. It challenges our classical intuition about space and distance. 2 geometries that appear radically different to a low-energy observer are revealed, through T-duality, to be indistinguishable to a fundamental string. This insight has reshaped our understanding of compactification, geometry, and the role of extra dimensions in string theory. Moreover, T-duality provides a map between type 2A and type 2B string theories. When compactified on a circle, one theory transforms into the other. What looks like a fundamental string in one description becomes a causet object in the other, and vice versa. A second class of dualities, known as S-duality, relates strongly coupled theories to weakly coupled ones. In quantum field theory, calculations often rely on perturbation theory, expanding physical quantities and powers of a small coupling constant. But when the coupling becomes large, perturbation theory breaks down, and new methods are needed. S-duality provides a profound shortcut. It states that a theory with strong interactions may be equivalent to another theory with weak interactions, allowing one to study intractable problems in one model by solving easier problems in its dual. In string theory, S-duality reveals unexpected equivalences. For instance, type 1 string theory and the heterotic SO32 theory, which appear structurally different, turn out to be dual to each other under a strong weak coupling transformation. The weakly coupled regime of one corresponds to the strongly coupled regime of the other. This discovery was not just an abstract conjecture. It was supported by precise calculations, symmetry matching, and consistency checks across spectra, anomalies, and interactions. It suggested that different string theories may describe the same physics, just observed from different energy scales or perspectives. S-duality also applies to type 2B string theory, which is self-dual. In this case, the theory at strong coupling is equivalent to itself at weak coupling. This self-duality implies that certain phenomena, like D-brane configurations or black hole solutions, have mirrored descriptions under the exchange of strong and weak forces. It also helps explain why type 2B theory supports certain extended objects, like D strings and D3 branes, which remain stable across all values of the coupling. Together, T-duality and S-duality form a powerful toolkit. But their true strength emerges when they are combined into more general relationships, sometimes referred to as U-duality. U-dualities mix geometric transformations like those of T-duality with coupling transformations from S-duality. These are more than mathematical curiosities. They provide clues to the existence of a larger, unifying framework in which all 5 superstring theories are embedded. This led to the emergence of a revolutionary idea that all 5 superstring theories are limits or aspects of a more fundamental theory, dubbed M-theory. The M remains deliberately ambiguous. It has been said to stand for mother, mystery, membrane, or magic, reflecting the theory's elusive nature. M-theory is believed to live in 11 space-time dimensions, one more than the 10 required by string theory. In this picture, the various string theories emerge from different compactifications or limiting cases of this higher dimensional structure. One of the earliest clues pointing toward M-theory came from studying the strong coupling limit of type 2A string theory. As the coupling grows, a new spatial dimension effectively becomes visible, and the strings give rise to more complex objects, specifically 2-dimensional membranes and 5-dimensional branes. These objects are not perturbative artifacts. They are essential, stable features of the theory. The behavior of these branes match the predictions of 11-dimensional supergravity, a known field theory that had long stood as a mathematical curiosity without a clear quantum interpretation. Now, it seemed to arise naturally as a low-energy limit of the full theory, M-theory. Similarly, the E8 times E8 heterotic string, when compactified on a small segment with specific boundary conditions, also produces a theory consistent with M-theory. These consistent reductions and correspondences built a compelling case. The 5 string theories were shadows of a single, higher dimensional reality, each capturing only a slice of the full picture. But M-theory remains incompletely defined. Unlike the 5 superstring theories, which have well-developed worldsheet formulations and perturbative expansions, M-theory lacks a complete microscopic definition. There is no universally accepted M-brain action analogous to the string action. Researchers often study M-theory through its low-energy approximations or by analyzing its various compactifications and dualities. Progress has been made using tools like matrix theory and holographic principles, but a full, background-independent formulation remains one of the greatest challenges in modern theoretical physics. Nonetheless, the dualities linking all 5 string theories and pointing toward M-theory have transformed the field. They have shown that concepts once thought rigid, like the number of space-time dimensions or the identity of fundamental particles, can be fluid and interrelated. In one regime, a string may appear fundamental. In another, it might emerge as a bound state of more elementary constituents. Brains that are heavy and rare in one picture may become light and ubiquitous in another. These insights have also reshaped our understanding of black holes, entropy, and quantum gravity. In some dual descriptions, black holes become configurations of brains and strings, allowing their entropy to be counted from first principles. The matching of microscopic states with thermodynamic quantities lends credibility to the duality framework and supports the idea that string theory, and by extension M-theory, can resolve some of the deepest puzzles in physics. In certain cases, dualities even blur the distinction between gravity and gauge theory. The AD-SCFT correspondence, though more directly tied to string theory in specific geometries, is one such example. It posits that a gravitational theory in a higher dimensional space is equivalent to a quantum field theory without gravity on its boundary. This holographic principle, which grew out of insights from string dualities, has found applications in fields ranging from quantum information to condensed matter physics. Despite this progress, much remains unknown. The precise nature of M-theory is still unclear. Its non-perturbative formulation is incomplete, and we lack a first principles description that unifies all known dualities under a single formalism. The deeper mechanisms behind these equivalences, and whether they stem from symmetry, topology, or something more abstract, remain topics of intense research. Yet what dualities have taught us is profound. That truth in physics may not reside in any single formulation. Instead, different perspectives may each reveal partial truths, valid within their own regimes, but pointing toward something larger. Reality, at its most fundamental level, may not be confined to a fixed language or framework. Instead, it may unfold through a web of interrelated descriptions, each casting light on different features of the same underlying structure. And in that recognition, we encounter a humbling lesson. The unity of string theories through dualities does not speak to simplicity, but to coherence, an intricate symmetry that binds diverse views into a larger whole. Perhaps the universe, too, does not choose one form of truth, but harmonizes many. What seems different may only be distant reflections, curved in a higher dimensional mirror we are just beginning to glimpse. Chapter 8. M-theory and the 11th dimension. As string theory matured and its internal symmetries unfolded, the growing web of dualities revealed something unexpected. The 5 superstring theories, once considered distinct frameworks, began to appear as shadows or facets of a deeper structure. This structure, not itself a string theory in the traditional sense, seemed to live in 11 dimensions and included not just strings, but higher dimensional extended objects such as membranes and brains. This unifying theory came to be known, tentatively and mysteriously, as M-theory. M-theory did not arise from a single eureka moment. Instead, it emerged incrementally from mathematical and physical evidence gathered through studies of strong coupling behavior in string theories and the symmetries revealed by dualities. Type 2a string theory, when considered at strong coupling, exhibits properties that cannot be fully explained in 10 dimensions. One of the earliest insights was that, as the coupling constant increases, a new spatial dimension effectively opens up. The strings begin to behave as one-dimensional slices of more complex two-dimensional surfaces, membranes. This hinted that the complete theory might require an additional 11th dimension to account for its true degrees of freedom. What emerged was a tantalizing possibility that the low energy limit of this 11-dimensional theory is none other than 11-dimensional supergravity, a framework that had long existed mathematically but had lacked a fundamental quantum justification. M-theory provided that justification. Supergravity in 11 dimensions, when compactified appropriately, reproduces the known 10-dimensional string theories in various limits. Thus, the higher dimensional theory was not separate from string theory, but a broader context in which strings, branes, and their dualities could coexist consistently. A central feature of M-theory is its inclusion of higher dimensional objects beyond strings. These include two-dimensional membranes, M2 branes, and five-dimensional analogs, M5 branes. In contrast to the one-dimensional strings, these branes are extended over more spatial dimensions and play a fundamental role in the dynamics of the theory. M2 branes can be thought of as fundamental excitations, much like strings, while M5 branes emerge as solitonic solutions with rich physical implications. The interactions and intersections of these branes are thought to give rise to many of the phenomena previously described in string theory, including gauge fields, dualities, and black hole microstates. The existence of these branes also ties M-theory to concepts of non-perturbative physics, phenomena that cannot be captured by expanding around a small coupling constant. While perturbative string theory relies on small fluctuations of strings, M-theory suggests that these are merely one aspect of a richer, inherently non-perturbative structure. This realization shifts the focus from the vibrations of individual strings to the geometric and topological properties of higher dimensional objects. In this view, what appear as particles or fields in lower dimensional space may emerge from the dynamics of branes embedded in the higher dimensional background. Compactification plays a crucial role in connecting M-theory to observable physics. Since we do not observe 11 macroscopic spacetime dimensions, the extra dimensions must be compactified, curled up into small, unobservable shapes. The geometry and topology of these compact dimensions influence the physics that emerges in lower dimensions. For instance, compactifying M-theory on a 7-dimensional manifold, known as a G2 manifold, can lead to a 4-dimensional universe with realistic features such as chiral fermions, gauge interactions, and supersymmetry breaking. However, constructing such compactifications remains a formidable challenge. The mathematical complexity of G2 manifolds is significantly greater than that of the more commonly studied Calabi-Yau spaces in string theory. Unlike Calabi-Yau manifolds, which preserve a specific type of supersymmetry and have well-defined moduli spaces, G2 manifolds are more rigid and less well understood. As a result, building phenomenologically viable models within M-theory has proven difficult, though progress continues in both geometry and physics communities. Another area where M-theory has proven insightful is in the study of black holes. Certain configurations of intersecting branes in M-theory can be interpreted as black holes from a lower dimensional perspective. Remarkably, these brane configurations allow for the counting of microscopic states corresponding to the entropy of the black hole, matching the Bekenstein-Hawking formula derived from thermodynamics. This agreement provides strong evidence that M-theory captures the quantum microstructure of space-time, even in the regime of extreme gravity. The influence of M-theory also extends into the realm of quantum field theory. Through the study of brane dynamics, M-theory provides new tools for understanding gauge theories in various dimensions. For example, configurations of M5 branes can be used to construct 6-dimensional superconformal field theories. which in turn reduce to four-dimensional gauge theories under certain compactifications. These connections have revealed deep dualities and correspondences within field theory itself, many of which would have been difficult to discover without the geometric perspective provided by M-theory. Despite its many successes, M-theory remains incomplete. Unlike the 5 superstring theories, it does not yet possess a complete action or world volume formulation. There is no analog of the string world sheet path integral for membranes or 5 branes that is fully understood and computable. Much of the work on M-theory has proceeded through indirect evidence, matching symmetries, comparing low-energy limits, and using dualities to infer consistency. While this has built a strong circumstantial case, the absence of a complete formulation leaves many questions unanswered. This limitation is particularly acute when trying to understand the dynamics of M-theory beyond supersymmetric or highly symmetric settings. In regimes where supersymmetry is broken or where quantum gravitational effects become dominant, we lack a comprehensive framework for calculation. This gap limits our ability to extract precise predictions from M-theory, making it difficult to test against empirical data. Still, some researchers remain optimistic that new mathematical tools, perhaps from areas like category theory, non-commutative geometry, or holography, may eventually provide the missing pieces. Holography, in particular, has emerged as a promising bridge between M-theory and lower-dimensional physics. The AD-S-CFT correspondence, a duality between a gravitational theory and a higher-dimensional anti-de Sitter AD-S space, and a conformal field theory CFT on its boundary, was originally formulated in the context of Type 2b string theory, but has since been extended to M-theory. In certain configurations, the dynamics of M2 branes or M5 branes give rise to ADS geometries, suggesting a dual description in terms of 3- or 6-dimensional field theories. These insights are not only deepening our understanding of M-theory, but also reshaping how we think about space, time, and information in quantum gravity. The 11th dimension itself, once considered a speculative curiosity, has become a vital component of modern theoretical physics. It is not just an extra spatial direction, but a conceptual space where distinctions between strings and branes blur, where dualities become symmetries, and where our understanding of space-time is stretched to its limits. In some formulations, this dimension is not fixed or static, but emerges dynamically, depending on the energy scale or the configuration of branes. This notion, that dimensionality itself might be an emergent property, represents a radical departure from traditional physics and could be a key to unlocking the next phase of theoretical development. Yet this progress has also revealed the enormity of what remains unknown. What is M-theory in its full quantum form? Can it be defined non-perturbatively, in a way that does not rely on limits or approximations? Is there a single unifying principle, a mathematical object or conceptual framework that gives rise to all known features of string theory, branes, dualities, and beyond? And perhaps most profoundly, does M-theory merely describe a mathematical structure, or does it point toward a physical reality deeper than what current experiments can probe? These questions do not have answers yet. But the pursuit of M-theory has already reshaped how physicists think about unification, geometry, and the very nature of reality. It suggests that the universe, at its deepest level, may not be composed of individual particles or even vibrating strings, but of relationships, symmetries, topologies, and dimensions woven together in a framework we are only beginning to glimpse. And perhaps this is the most humbling realization of all, that the 11th dimension is not just a direction in space, but an invitation to think beyond what we know. That the structure of the universe may not present itself through isolated theories, but through a tapestry of perspectives, each reflecting part of an unseeable whole. And that somewhere, beyond the equations and geometries, lies a unity not just of matter and energy, but of understanding itself. Chapter 9. String Theory and Gravity. Among the many puzzles that theoretical physics has attempted to solve, few are as enduring and as daunting as the challenge of reconciling gravity with quantum mechanics. Gravity, the force that governs the motion of planets, stars, and galaxies, is well described by Einstein's general theory of relativity. This classical theory interprets gravity not as a force transmitted through space, but as the curvature of space-time itself, shaped by the presence of mass and energy. On the other hand, the other three fundamental forces, electromagnetism, the weak force, and the strong force, are encapsulated in the quantum field theoretic framework of the Standard Model. These forces arise from the exchange of quantum particles and are governed by the principles of uncertainty, superposition, and gauge symmetry. The problem is that general relativity and quantum mechanics, while immensely successful in their own domains, are mathematically incompatible when brought together. Attempts to quantize gravity using the same methods that work for the other forces result in nonsensical infinities and loss of predictability. This breakdown becomes especially acute at the smallest scales, near singularities such as those inside black holes or at the origin of the universe, where quantum effects should dominate, but classical gravity still plays a central role. Bridging this divide requires a quantum theory of gravity, a framework that describes how the gravitational field behaves when quantum effects cannot be ignored. String theory emerged as a leading candidate for this unification, not by design, but by discovery. Initially conceived as a model to explain the strong nuclear force, string theory was later recognized to contain within it a natural description of gravity. In the 1970s, researchers found that among the spectrum of vibrational modes of the string, there existed a particular excitation that had the properties of a massless spin-2 particle. This particle, by all known criteria, behaves like the graviton, the hypothetical quantum particle that mediates the gravitational force. What makes this result extraordinary is that the graviton was not artificially introduced or postulated. It arises necessarily from the mathematics of the theory once consistency conditions are imposed. To avoid mathematical anomalies and ensure the theory is unitary, that is, probabilities always sum to 1, string theory must include a graviton-like state. In this sense, string theory does not merely accommodate gravity, it predicts it. This feature sharply distinguishes string theory from quantum field theories, where gravity remains stubbornly outside the framework. Moreover, string theory modifies the behavior of gravity at short distances in a way that is both natural and non-singular. In general relativity, interactions at a point, like two particles colliding, can lead to infinite curvature or energy density. But in string theory, particles are not point-like, they are tiny loops or segments of string. This extended structure smears out interactions and softens the infinities that plague quantum gravity. When two strings approach each other, their interaction is spread across a finite region, avoiding the ultraviolet divergences that would arise from point interactions. This built-in regularization is one reason why string theory is considered a consistent candidate for a theory of quantum gravity. In addition to smoothing out divergences, string theory also introduces new dynamical objects, such as D-branes and higher dimensional membranes that can gravitate and interact. These extended objects provide further avenues for modeling gravitational phenomena. For example, black holes can be modeled as collections of branes, whose microstates can be counted in certain configurations. These calculations have successfully reproduced the Bekenstein-Hawking entropy formula for black holes in specific supersymmetric scenarios. While these models do not yet cover all known black holes, especially those without supersymmetry, they offer a path to resolving the long-standing mystery of how gravity encodes information. Another way string theory addresses gravity is through its unifying geometry. In general relativity, Space-time is dynamic, bending and stretching in response to matter. String theory retains this view, but adds new layers of structure. The shapes and topologies of the extra dimensions in string theory determine the types of particles and interactions seen in the lower dimensional world. The gravitational field is encoded in the geometry of the full 10 or 11-dimensional spacetime. This geometric picture is more than aesthetic. It tightly binds the gravitational field to the quantum properties of strings and branes. One of the most striking developments in recent years is the emergence of holographic duality, a relationship between a theory of gravity in a higher dimensional spacetime and a quantum field theory without gravity on its lower dimensional boundary. This correspondence, often referred to as the AD-S-CFT correspondence, arose from string theory and provides a non-perturbative definition of certain string theories. In this framework, gravitational dynamics in the bulk spacetime are encoded in quantum interactions at the boundary. This duality has allowed physicists to study aspects of quantum gravity by analyzing much simpler, non-gravitational field theories. Holography reveals a surprising possibility that gravity may be an emergent phenomenon. Just as temperature and pressure emerge from the collective behavior of molecules, spacetime and its curvature might arise from more fundamental, non-geometric degrees of freedom. This idea turns the traditional understanding of gravity on its head. Instead of being a fundamental force, gravity might be a large-scale consequence of microscopic quantum interactions, an approximation valid only when viewed from a certain distance or energy scale. This line of thinking also provides a potential resolution to the black hole information paradox, the apparent contradiction between the predictions of general relativity, which suggests information is lost in black holes, and the unitarity of quantum mechanics, which forbids such loss. Within the string theoretic and holographic context, it appears increasingly likely that information is preserved, encoded in subtle correlations across the event horizon, or recovered through Hawking radiation when described in a complete quantum theory. However, despite its elegance and theoretical consistency, string theory's connection to gravity remains largely untested in experimental terms. The predicted strings are exceedingly small, far beyond the reach of current particle accelerators. Moreover, many predictions of string theory are model-dependent, relying on specific choices of compactification geometry or brane configurations. This vast landscape of possible solutions makes it difficult to extract unique, testable predictions. As a result, some critics argue that string theory's successes in unifying gravity and quantum mechanics remain largely theoretical. Nonetheless, its success in providing a mathematically coherent framework for quantum gravity cannot be ignored. It is the only known framework that successfully combines gravity with the principles of quantum mechanics in a way that remains self-consistent across all energy scales. It avoids the ultraviolet problems of quantum field theory and explains the existence of the graviton without additional assumptions. It provides a roadmap for understanding black holes, cosmology, and the possible origins of spacetime itself. There are also compelling hints that gravity, as described by string theory, is deeply intertwined with thermodynamics and quantum information. The observation that black holes have entropy and temperature, along with the discovery that spacetime geometry might be shaped by entanglement entropy in a dual quantum field theory, suggests that gravitational dynamics might emerge from statistical or information theoretic principles. This view, still in its early stages, is beginning to reshape the very definition of what gravity is. Moreover, string theory's gravitational predictions extend into cosmology. Models of the early universe, such as inflation, have been explored within the string theory context, although finding a stable, realistic vacuum with positive cosmological constant remains challenging. Some proposals, like the string landscape and eternal inflation, attempt to explain the observed properties of our universe as statistical outcomes of a vast ensemble of possibilities. While these ideas are controversial, they underscore the central role gravity plays in the quest to understand not just how the universe works, but why it appears the way it does. At the heart of all these developments is a profound reinterpretation of gravity, not merely as a force or a field, but as an emergent, dynamic feature of a deeper quantum structure. In this view, Einstein's curved spacetime is not the bedrock of nature, but a large-scale illusion arising from a fabric of extended objects, quantum entanglements, and hidden dimensions. And perhaps, as we follow the vibrations of strings and the contours of compactified space, we are not just exploring the mechanics of gravity, but the architecture of reality itself. Gravity, in this light, is no longer the final puzzle piece. It is a window into how the universe builds itself from the ground up, from the hum of quantum fields to the sweep of galaxies. And through that window, if we dare to look long enough, we may see something more than particles and forces. We may see a universe that is not only governed by laws, but shaped by deeper symmetries, woven not from matter, but from meaning. Chapter 10. Challenges, open questions, and current research. String theory has grown into one of the most ambitious and mathematically rich frameworks in theoretical physics. It promises a unified picture of all fundamental forces, naturally includes gravity, and links deeply with geometry and topology. But despite decades of development and theoretical successes, string theory is not yet a complete or empirically verified theory. In fact, it raises as many questions as it answers. The frontier of string theory is shaped as much by what remains unknown as by what has been discovered. In this chapter, we examine the major challenges, persistent questions, and ongoing areas of research that continue to define and propel the field. One of the most significant challenges facing string theory is the lack of experimental evidence. Unlike quantum electrodynamics or the standard model of particle physics, string theory has not yet yielded any direct predictions that can be tested with current technology. The characteristic scale at which string effects become noticeable is believed to be close to the Planck length, far smaller than what can be accessed by particle accelerators such as the Large Hadron Collider. This makes it extremely difficult to verify or falsify the theory through traditional high-energy experiments. While some speculative ideas suggest indirect signatures, such as the presence of extra dimensions or modifications to gravity at short distances, no conclusive evidence has been observed. The vastness of the string landscape compounds this issue. String theory allows for an immense number of possible vacuum solutions, ways to compactify extra dimensions and stabilize fields. Each solution corresponds to a different effective low-energy theory with its own particle content, symmetries, and constants of nature. While this landscape makes string theory flexible enough to potentially accommodate our universe, it also raises the problem of predictability. Without a clear mechanism for selecting one vacuum over others, the theory risks being untestable, as almost any observed result could be compatible with some point in the landscape. This leads directly into the problem of vacuum selection. What mechanism, if any, determines which vacuum describes our universe? Are we living in a unique, dynamically selected vacuum, or one chosen at random from a multiverse of possibilities? Some proposals suggest that anthropic reasoning may play a role. Perhaps only certain vacua allow for the existence of observers like us, and our universe is one of those. While the anthropic principle has some explanatory power, it remains controversial. Many physicists are uncomfortable with it, as it sidesteps the goal of predictive and falsifiable science. Another open question involves the formulation of string theory itself. Despite its many versions and dualities, string theory lacks a complete non-perturbative definition. Most of what is known comes from expansions around specific backgrounds or limits where calculations are tractable. In these regimes, one can work with conformal field theories on the world sheet or use the tools of supergravity. But there is no single action or set of equations that encapsulates the full theory across all backgrounds and coupling strengths. This incompleteness limits our understanding of the deep principles behind string theory and restricts our ability to explore genuinely new physical regimes. The same holds for M-theory, which, although central to unifying the 5 string theories, is even less understood in full. Much of our knowledge of M-theory comes from indirect evidence, consistency checks, dualities, and low-energy limits that agree with known results. A complete formulation of M-theory would likely clarify the fundamental degrees of freedom and symmetries underlying string theory. Whether M-theory requires a new kind of mathematics or a new approach to space-time itself remains an active and open area of inquiry. Progress in string theory has also highlighted the potential emergence of space-time. In many scenarios, particularly those involving holography, space-time geometry appears to arise from more fundamental non-geometric data, such as entanglement patterns or gauge-theoretic configurations. If space and time are emergent, not fundamental, it raises profound questions about what constitutes a location, a distance, or even a moment. These ideas push the boundaries of how physics has traditionally been formulated and suggest that our classical understanding of the universe may be only an approximation of a much deeper quantum structure. This brings us to another major open area, the nature of time in string theory. While the theory treats time as a parameter in many formulations, its deeper status is uncertain. In some backgrounds, time seems to emerge or disappear altogether. Time-dependent solutions, such as those that model cosmological evolution or transitions between vacua, are particularly challenging to analyze. A full understanding of quantum cosmology within string theory is still lacking, and many of the tools developed for static or asymptotically flat spaces break down in expanding or dynamic universes. String theory's complexity also poses a technical challenge. The mathematics required to work with compactified manifolds, moduli spaces, and conformal field theories is highly non-trivial and often only partially understood. Some important areas of string theory depend on advanced concepts from algebraic geometry, category theory, and topology. While this interplay has generated fruitful collaborations between physicists and mathematicians, it also makes the theory inaccessible to all but a small subset of researchers. Progress is often incremental and contingent on the development of new mathematical tools or the translation of physical intuition into rigorous formalism. Despite these challenges, active research continues on many fronts. One area of progress is in the study of string dualities, transformations that relate seemingly distinct theories. These include S-duality, T-duality, and mirror symmetry, among others. Dualities not only reveal hidden symmetries, but also provide calculational tools. By translating difficult questions in one theory to easier ones in a dual description, physicists can gain new insights. Dualities have also led to surprising results in quantum field theory, including exact results for quantities and supersymmetric gauge theories that were previously thought to be intractable. Another thriving area is the study of black holes in string theory. Certain configurations of D-branes can be used to model black holes, and in some cases, researchers have successfully counted the microstates corresponding to the black hole's entropy. These results offer a microscopic foundation for black hole thermodynamics and point toward a resolution of the black hole information paradox. Although the full story remains incomplete, especially for non-extremal or evaporating black holes, the progress made so far suggests that string theory is equipped to address some of the deepest puzzles in gravitational physics. Cosmology is another frontier. String cosmology attempts to embed models of inflation, dark energy, and the early universe into a string-theoretic context. While this is complicated by the difficulty of stabilizing moduli and generating realistic vacua, some proposals, such as string gas cosmology and the landscape multiverse, offer intriguing paths. However, connecting these ideas to observable cosmological data remains a formidable task. Research is also expanding into the study of emergent gauge theories, the use of topological string theory to understand non-perturbative effects, and the development of string field theory as a potential avenue to a more complete description. Other directions include exploring the role of quantum entanglement in defining geometry via the ADS-CFT correspondence, and investigating how entropic gravity or tensor networks might offer new views on the emergence of spacetime. Moreover, holography continues to play a transformative role. The idea that a gravitational theory in a higher dimensional spacetime can be equivalent to a non-gravitational theory in lower dimensions has opened entirely new ways of thinking about information, quantum chaos, and thermodynamics. Applications of holographic duality now extend beyond high-energy physics into condensed matter theory, where it is used to model systems with strong interactions or exotic quantum phases. A newer research avenue explores celestial holography, a proposal to reformulate scattering amplitudes in quantum gravity using a kind of holography based on the celestial sphere at infinity. This approach aims to uncover a more universal formulation of quantum gravity that works even in flat spacetimes, potentially broadening the reach of holography beyond its original ADS-CFT domain. String theory has also provided deep connections with pure mathematics. Concepts developed within string theory have led to discoveries in enumerative geometry, mirror symmetry, and the classification of Calabi-Yau manifolds. In some cases, predictions from physics have guided mathematicians to results they would not otherwise have found. This cross-pollination continues to enrich both disciplines. Yet for all these advances, string theory remains a work in progress. It is a framework with immense potential and a vast landscape of possibilities, but one that still lacks a final, universal formulation. Some researchers continue to search for an underlying principle, a deeper foundation from which all of string theory might be derived. Whether this principle is geometric, algebraic, informational, or something else entirely remains unknown. And so, the search continues. In laboratories, chalkboards, and notebooks, physicists trace out paths through the jungle of mathematical complexity, following the trails left by symmetry, duality, and logic. Each new result, each simplification, each subtle hint of structure, feels like a piece of a puzzle that is still coming into focus. And perhaps that is the nature of truth at the deepest level. It does not arrive in a single formula or revelation, but accumulates gradually, refracted through perspectives that grow with time. String theory may not yet be the final word in physics, but it may be a necessary step toward whatever comes next. A scaffold for the next leap, or a mirror showing us that the laws of the universe may be less about particles and more about patterns. Not answers, always, but questions asked more clearly than ever before. Thanks for staying with me, friend. Whether string theory turns out to be the final theory or just one chapter in a much longer story, the journey to understand it brings us closer to something deeper. Until next time, sleep well and sweet dreams among the stars.